No one. Yeah, that's going to be too much of distraction.
Yeah, I always like to ask though. So, no problem at all.
All right, good morning. Okay, that was pathetic. Let's try again. Good morning. That's much better. All right. So we're going to look at section 2.2 today. We'll be looking at this thing called the limit of a function. We're getting into the foundation of calculus now, together with the limit and what we saw last time. We're finally getting the start of the basics of calculus. Okay, so let's look at this function here. F of x is equal to the square root of x plus 4 minus 2 over x. Now, if you look at this function here, one thing that's very obvious right away is that x can be a lot of things, but x can never be equal to 0 exactly because of the denominator down here. But as long as I stay away from x is equal to 0 exactly, in principle, I can use any value as close to x as I want to. But x can be made to be you'll see this word a lot today, can be made to be arbitrarily close to 0. Arbitrarily means that as close as you want to and even more, right? So the question we want to investigate here is we can't let x be 0. But if we let x be really, 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 really close to 0, what is this function eventually going to do? And we'll do this in a very, very simple way. Let's make a big table here. And on the top row here, I'm going to collect a few values of x that are close to 0. And I want to approach 0 from either end of it. So I'm going to start with x is equal to negative 0.1. That's pretty close to 0, but we can get closer. And I'll keep going, getting closer and closer to 0. First from the left side. Okay, so these are just not random, but numbers of x that I've chosen that are close to 0. And then on the other side, I look at what the function is doing as I approach x from the left side of 0. I want to see what's going on as I approach 0 from the right side. And I'm going to mirror these values but make them positive. And I use a tenth, 100th, 1,000, and so on. But in principle, you can use any value you want, just as long as they're getting closer, progressively close to the target, which is 0. Clearly, we cannot be right here. This is not a place where the function is defined. But everywhere else, no matter how close we get to 0, we can find a value. Okay, so if I take negative 0.1 and I plug it into here, I get square root of 3.9 minus 2 over negative 0.1. And what I get out is 0.25658. Sorry, 25658. I rounded a little bit. I can get even closer to 0 by cutting the distance from here to here by a factor of 10, right? And if I plug in this number into here, I get 3.99 under root minus 2 over negative 0.01. I end up getting 0.25 0.016. If I keep going, this will give me 0.25 0016. I keep going, I get 0.25, 3 zeros, and then 16. Okay, now I've kind of discovered what the function is trying to do as we make x progressively close to 0, first from the negative side, the left side of that number. I'll do exactly the same thing with the numbers from the other side of 0, starting with 0.1. And we do exactly the same thing we did before. 0.1 becomes x, and I get radical 4.1 minus 2 over 0.1. And I get 0.24846. And by the way, this kind of problem, obviously, you need a calculator to do. But on quizzes and exams, we won't have anything. The function will be such a way, and the numbers will be such a way that you can calculate without using a calculator. But for homework and class examples, these examples are fine. Okay, I repeat this. 0.01 into here, and I end up getting 0.24984. Keep going. I get 0.249984. And then one more here, we get 0.249984. All right, so these 8 values here should be enough to give us some kind of idea what the function is trying to do as we make x progressively close to 0. But obviously, we cannot be at 0. And looking at these numbers here, especially these 2, and the progression overall, what do you think that the function is trying to become as we get closer and closer to 0? looks like 0.25, right? A quarter. These are about the same away from 0.25. So looks like what? Looks like f of x is approaching 0.25 as x approaches 0. Sometimes we can't be sure about 0.25 exactly, but at least we can say that it's probably going to be in the neighborhood of 0.25. Now this number right here, this 0.25, this is what's called a limit of a function. And I'll write that down. So that thing is called the limit of this function radical x plus 4 minus 2 over x as x approaches 0. We want to use a shorthand notation for this kind of statement here. So we write LIM for limit. And underneath this lim, LIM, I want to write down what x is trying to do. X is getting closer and closer to 0, so we write x approaches, the right arrow, 0. And then we write a function next to this thing right here. The limit of the function radical x plus 4 minus 2 over x as x approaches 0 is equal to 0.25. All right, so these two statements are equivalent, and obviously the mathematical notation is a much more compact and much more convenient one to use. But make sure you understand what it's telling you in words. In general, you would write x approaches some number a. 0 is just one particular value that x can go to. You can let it go to any value that you want it to go to. So x is equal to a, approaches a of whatever the function you're looking at. And the right-hand side is the limit. We use L usually to denote that. What this means right here, similar to the example we just saw, this means that we can make the function f of x as close to L as we want. By making x sufficiently close to a, but not equal to a. If you look at the example we just did, I can make this number as close to 0.25 as I want by keep making the x number smaller and smaller. In fact, what this is saying is that you can specify how close you want this to get to 0.25, within a tenth, within a thousandth, within a millionth, for example. If you specify how close you want it to be, we can always find a value of x that can make that happen. And if you make that requirement even smaller, we can find another x to meet that requirement. Okay, so this is the function, the limit of a function. We write it this way: limit LIM underneath x arrow a, the function, and the right-hand side, whatever the number that the function appears to be trying to get close to. Questions? Okay, let's do a couple more examples. We'll look at this one right here, a little simpler. One over x minus 2, the whole thing squared. Just like in the last example, very obviously we spot right away that x cannot be equal to 2. But I can make x as close to 2, arbitrarily close to 2. If we do that, what is this function 1 over x minus 2 trying to do? Same kind of thing we're doing as we did in last example. Now for now, let's do just the very basic stuff. Just make a table and try to see the progression of the values. Eventually, we're going to learn ways to make this process go faster. But right now, let's focus on just the basic procedures. So again, I'm going to make a bunch of table here, choosing a bunch of values close to 2, and then finding out what the function 1 over x minus 2 squared is trying to do. I like to choose 4 values on each side of the target, but you could get away with maybe 3, maybe even 2, depending on what the function looks like. But for my examples, I'm going to use 4 values on each side of that target. I can approach the number 2 from the left side of 2, something smaller than 2. So let's say we start at 1.9. And that puts me at 0.1 away from the target. Then, like last time, I'll cut the distance by a factor of 10 each time. We want to get to 2, but we can't get there. And then from the right side of 2, yeah. I did the same thing. Oh, I missed out the 9. Sorry. There we go. Thank you. Thank you. And then on the other side, again, I'm choosing 4 values. And I'm going to mirror what I did on the left side. You don't have to. It's just something that's easy to do. 2.1. So cut the distance by a factor of 10, just like I did on the left. 0, 0, 0, 1. Triple 0 and a 1. Got a problem right there, so we got to stay away from 2, exactly 2. But I can make this as close to 2 as I want to. Okay, just like last time, now I take x is equal to 1.9. Put into here, I get 0.1. Negative 0.1 squared, that is 100. So 0.01, sorry. 1 over that is 100. If I put in 1.99 into here, square that, 1 over that, gives me 10,000. This gives me 1 million. And this one gives me 100 million. 100, 6 zeros after that. There we go. All right. Now on the right side, same thing. If I let x be 2.1, plug into here, calculate that, I get 100, 2.01, I also get 10,000. In fact, these numbers mirror each other. This is 1 million, and this is 100 million. Can you read those numbers okay? The small number, they're actually huge numbers, but I wrote them small. Right? The small, big numbers, can you read them okay? Okay. All right, so as we make x closer and closer to 2, it looks like f of x is trying to get bigger and bigger. If I cut this distance by a factor of 10 again, this thing is going to be even bigger than 100 million. In fact, based on what we're seeing here, we can make the f of x value as big as we want simply by making x as close to 2 as we feel like. So we can say here, I'll write down what I just said. This function becomes arbitrarily large as x gets close to 2. And in the shorthand mathematical notation, you would write the limit LIM x goes to 2, the function we're investigating. And how would you represent a big number? Infinity, right, exactly, infinity. There's no bound to how big you can make it. So we say the limit is infinity. This is what's called an infinite limit. If the limit appears to go to a very large negative number, you would write the limit as negative infinity. But either way, infinity or negative infinity, we say that is an infinite limit. You can make it as big as you want simply by making x as close to 2 as you want without letting x be exactly equal to 2. Question? That's right, yeah. We have a fixed number on the top, but the denominator, like you said, is getting smaller and smaller. Dividing by a progressively smaller number becomes a progressively large number. Yeah. Okay? Keep in mind that we can make x close to 2, but not equal to 2. It's like in basketball when you want to shoot a three-pointer, your foot can be as close to that line as you want, right? But as soon as you touch that line, that's a 2 now. So same thing here. You can get as close to 2 as you want, even if the function contains that number in its domain. When we look at the limit, we don't want to be at 2, even if we could be at 2. We'll see an example of that in a little bit. Okay, now I'm going to make a slight change to this function. I'm going to remove this square from x minus 2. I'll just make it simply 1 over x minus 2. And let's again look at the limit. I'm just going to duplicate what we did last time. Exactly the same 8 values in the table. And so I'll go kind of quick because we essentially did this already. .999. One more. 2 can't be there, but that's okay. All right, so exactly the same set of 8 x values. And we'll do the same thing. Now, one thing we can note right away without actually carrying these out is to see that the same general behavior is going to show up. The denominator is going to get progressively smaller. However, by removing the square, we're changing the sign of what's in the denominator. So it's going to change the sign of all these y values. When we do that, here's what we get. If I take 1.9 into here, I get 1 over negative 0.1. I get negative 10. If I put that into here, I get negative 100, negative 1,000, negative 10,000. They're smaller, but still getting progressively bigger, but negative this time. For the right-hand side, this will give me a 10, 100, 1,000, and then 10,000. Okay, so the first thing we note here is that what the function 1 over x minus 2 is doing depends on which way we approach 2. From the right, these numbers get bigger and bigger. From the left, they also get bigger, but they are always negative. Right side gives me something, left side gives me something else. When this happens, when these two sides don't reach a common point, common place they're trying to get to, we say that the limit does not exist. You want the behavior to be the same no matter which side you approach from. From the right, from the left, it doesn't matter. When you take 261, Calc 3, when you look at three-dimensional objects, three-dimensional functions, then you have not just 2 ways of approaching that point, you have infinitely many ways. Think about a three-dimensional point. You can approach from the right, left, up, down, northeast, and all that. So the same idea carries over when you take Calc 3, but right now we're looking at just a planar kind of thing, very, very simple. When this happens, when they don't agree, we say the limit does not exist. In the shorthand notation, you would write DNE for does not exist. Don't write an equal to DNE. It's not a number you can't make it equal to. Just write the limit, the function, does not exist for DNE for does not exist. Now, however, we still want to give some kind of indication of what the function is doing. So we can look at just one side at a time. If I just want to focus on the right side of the function, I would write LIM, x, right side of the point, x approaches 2, and I put a superscript plus. That indicates I'm looking at the right side approach. And if I'm looking at the right side approach, I ignore what the left is doing. And if this is all I see, then my conclusion is that the value 1 over x minus 2 is getting as large as we can make x close to 2. Right? So from just the right side alone, we would say that this is trying to go to infinity. So let me write down a couple of things here. Superscript means from the right side, something bigger than the target. Coming from the left side, something smaller than 2. Now we ignore what's going on the right, and based on the trend of these values, we can say it's going to negative infinity. This will just keep growing but remaining negative. And these are called one-sided limits. Okay? So the proper limit does not exist because the values don't match. But the one-sided limits exist. Right side gives me an infinity, left side gives me a negative infinity. Any question on this? Yeah. Right. Absolutely. Yeah. So this is 1 over x shifted right by 2 units. And if you know what 1 over x looks like, then you know what 1 over x minus 2 looks like. So you can come to the same conclusion. Right? Were you going to say something else? Sure. You can explain this by making a table like we did here, or by sketching it, which I'm actually about to do. So you can explain this in a bunch of different ways. Other questions? All right. So his question was actually very timely. I was about to make sketches of these things. If you could sketch the graph, at least a rough but reasonably accurate graph, then you can get the same kind of conclusion here. The function 1 over x minus 2 squared is the same as 1 over x squared, but shifted to the right by 2 units. Two is a vertical asymptote. A vertical asymptote occurs, you remember, when the numerator is not 0, but the denominator is 0. So you got something, a regular number dividing by 0, that's when a vertical asymptote is going to occur. And then we're going to get these two kind of things on either side of that. And when you look at the limit, x approaches 2 of that function, on the graph, what you do is you just follow the graph while making x as close to 2 as you can. So imagine if you're walking on this branch right here, and you want to make x close to 2. So you would just follow this path right here, making x as close to 2 as you can. And then you want to look at what y is doing as you make x close to 2. As I bring x closer and closer to 2, let's look at the right-hand side limit first. So a plus. If I make x as close to 2 as I want to, I see that it just keeps making y, the f of x value, bigger and bigger, getting close to the asymptote. So for this function here, we can say that the right-sided limit will be infinity. While making x close to 2. And we see what y is doing. The left side limit, same idea. So this time I will walk close to 2 by following the left branch. And I'm constrained to walk on this path right here. The only thing I have control over is how close to x I want to be. And I can make x as close to 2 as I want to, following the path. And if I do that, the y value gets carried toward infinity, as we can see here. If these two are the same, then whatever they're getting to would also be the regular limit. The regular limit with no superscript. They're the same thing, so whatever they're trying to get to, that would also become the regular limit. The regular limit exists only if these two are the same. But the regular limit can fail to exist while these two still exist, like the last example we saw. Does that make sense? Questions? Okay, let's do another example with graphs. Well, one graph. Okay, I'm going to sketch a graph here whose equation we don't know, but actually it is not relevant at all. Okay, so here we go. got this graph. Equation is unknown but irrelevant. Well, first of all, does everybody remember the difference between the open circle and the solid dot? Yeah, what's the open circle? Not in the domain, right? What about the solid dot? That's where the function actually is defined. That's right. So this function is at x is equal to 2. The function is defined at 3, right? F of 2 is equal to 3. But there's a gap right here. And you can't have both points exist on the graph. So one of these cannot be there. Same thing here. The function looks like it should be there, but actually somehow we define the function to be at 2 when x is equal to 4. Okay, so let's look at a couple of limits here. First of all, what would the limit be as x approaches 2? Does not exist, and why is that? Right, absolutely. So you're right, does not exist. Because, remember, if what the function is doing depends on how you approach your target, then they are not going to meet, right? So therefore, the limit is not going to exist. Because what f of x does depends on how you approach. X is equal to 2. They don't meet at 2. So in this case, on a graph, you will see some kind of gap like that. Coming from the left, we can make x as close to 3. Make f of x as close to 3 as we want by making x close to 2, but smaller than 2. Coming from the right, we can make f of x as close to 2 as we want by making x close to 2, but something bigger than 2. Okay? Even though the regular limit does not exist, it is still meaningful to talk about one-sided limits. The limit x approaches 2 from the right side, As I follow this green path right here, when I get closer and closer to 2, y becomes closer and closer to 2. Okay? So that's the right-sided limit. And coming from the left, I only pay attention to this portion of the graph. I follow that path and then by making x close to 2 from the left side of 2, I can make y as close to 3 as I want to. The fact that I could actually be at 2 is completely irrelevant. All we want to do is to get close to 2. The fact that you are physically allowed to step on the three-point line is irrelevant when it comes to, well, it's relevant when you want to shoot a three-pointer, but you don't want to do that. Even though you're physically allowed to do that, for what you want to do, you don't want to touch that line. Same thing here. We are physically allowed to be at 2, but for the purpose of finding a limit, that is completely irrelevant, and we want to stay away from 2. But we can get as close to it as we want to. And as we get there, y gets closer and closer to 3. Okay? So the regular limit does not exist, but the one-sided limits exist. One is a 2, one is a 3. And if you see them being different numbers, then the regular limit will not exist. What about the limit as x approaches 4? 3.5, 2? Why not 2? I can't be at 4. When I get exactly equal to 4, I get a 2. So why is the limit not 2? Exactly, like we just talked about, we're not talking about being at exactly equal to 4. We're talking about getting close to 4. The fact that I could be at exactly equal to x is equal to 4 is completely irrelevant when it comes to limit. As I get closer and closer to 4 without being at 4, the y value gets closer and closer to 3.5. Okay? The fact that x can be 4 is irrelevant. Limit x approaches 4 means x is close to but not equal to 4. So that dot, wherever that dot is, even if the dot doesn't exist, is completely irrelevant when we look at this question right here. The limit as x approaches 4, what the function is trying to do. This is just like the earlier examples we did. Right? The first example we did here, we can't make x at 0, but I can define the function to be something at x exactly equal to 0. Even if I do that, the limit wouldn't change. We're still asking what happens when x is close to 4, 3.9999999, and not exactly equal to 4. If the regular limit exists, that is automatically also the two one-sided limits. If that limit exists, that implies that it doesn't matter which way you approach, you'll always get 3.5. So the limit from the right is going to be 3.5. And the limit from the left is also going to be 3.5. Okay? So if they are different, then the regular limit does not exist. Conversely, if the regular limit does not exist, that can mean that the two one-sided limits are not the same. If the regular limit is whatever it is, that is automatically the same for the two one-sided limits, because that can only exist if these two are the same thing. Okay, any question on this example? Okay, then we'll end it there today. That's it. Remember, I have no office hours today and no office hours on Friday. Feel free to email me with questions if you want, but just this week I won't have office hours for the remainder of the week. See you tomorrow. No, see you Friday.